So my name is Guilhem Larrieu. I'm a CNRS researcher at LAS, which is a laboratory in Toulouse. So I'm not a chemist. I'm not from computer science. I'm trying to develop micro and nano system for nanoelectronics or logic and memory, and also biointerfacing. So today I will take you on a journey from electron to molecule. And over the past 5 decades, semiconductor technology have fueled the information age. But as data volume exploded, we need to rethink how and where we store the information. So, as everybody knows, DNA is emerging as a radical alternative. So starting from beginning of this century, at that time, the entire world produced about a few hundred terabytes per day. If we are looking now, we are generating the same amount of data every second. So this curve here from IDC show an exponential growth where no existing data technology can follow. Because the world storage infrastructure only scale linearly, so where the data generation scaled exponentially. And on the top of that, the data we are never used still cost energy to maintain. So this is what we call cold data. So archive, backup, video, image, even raw data from your experiment are kept alive almost every time. On different supports, so magnetic disk or in a bay in a data center. So the goal is to try to think where we can put this information passively without energy consumption, in order to massively reduce the impact on carbon emission. So here, this is the diagram of the memory hierarchy you may all know. So from the very top, the CPU register, the CPU cache, down to the hard disk, for instance. So DNA in this kind of hierarchy will not replace any of this level, but extend the hierarchy. So it will be a new bottom layer from archival storage, where we can have a slow writing, slow reading, but very dense and stable data retention. So the vast majority here of digital information sits either just like photo or archive. So for this kind of cold data, speed is much less important than stability and density. So this is why DNA is a perfect fit for this. And if we have a look on the different supports that are using currently, we can see that magnetic hard drive is still the main use support, but some alternative memory formats have emerged. In particular, here, the portion of SSD increase a lot in recent time. So maybe some of you are not familiar with this kind of format. So flash memory replace what we use for a while, the moving part. So here we replace with electrons. So no mechanics, no friction. So compared to the conventional HDD, flash memory have 2 decades faster access, is shockproof, silent, and lower energy. And this change in type of format enable, for example, the rise of smartphone SSD, edge computing, and so on. So this translation marked what we call the first real memory revolution since the magnetic disk era. So how it works? What is it, a flash cell? So a flash cell is a MOS device. A MOS is a transistor, metal oxide semiconductor. So in very short, a MOS has 3 terminals, 2 contacts where the current is flowing from one to the other one, and a gate contact controlled by electrostatic, the channel, so the current flowing from one terminal to the other one. So this is how works a conventional MOSFET. And flash memory is a kind of modified MOSFET where we can store, in this level, at the dielectric level of the gate, we can store electrons in this insulated region. And when we store electrons, we can see a shift in the threshold characteristic. So the data bit 1 or 0. And we can, each bit is non-volatile because we don't need energy to store the information, and we can read this kind of memory without modifying the store information. So in short, we have 2 main devices, floating gate charge, where the electrons are stored in the polysilicon island, or charge trap flash, where the electrons, like this example, are trapped in a nitride layer. So to program one, for instance, we need to use a high voltage that will drive an electron through the gate oxide in order to store in the storage node. And to erase, we have to do the reverse operation, so the voltage polarity is reversed to remove the electron from the storage node to the other side. So we can understand that each cycle slightly damages this physical oxide, meaning we have a finite endurance, around 10 to the 4, 10 to the 5 in the best case. So with flash memory, we need to balance between speed, reliability, and retention. Now, as a lateral scaling hits physical limit, this is the case for logic, for transistor device. It's around, in planar, around 15 nanometer. But this is also the same for memory industry. So industry first went to vertical. So now we have this 3D DOM stacks memory cell on a pillar. You can see in red the pillar. So through multiple oxide nitride layer. So of course the benefits, we have a much higher density, lower cost per bit, and better endurance. So Samsung and Toshiba starting this kind to introduce this kind of technology in 2013, and now it became an industry standard. And to move a little bit in complexity, with this kind of flash memory, now we can store 2, 3, even 4 bits per cell. So we can understand that we can save a lot of space. And in this case, its bit correspond to a much narrow voltage window. So this requires extremely precise read, but also write control and advanced correction. So now we need to balance what we call software-hardware co-optimization in order to deal with correction error and design. Here we can see the evolution of flash memory with the density, with the scaling, and we are reaching a physical wall, because we need to, from one generation to the other one, make the oxide thinner, meaning more tunnel leakage, and we have high loss of retention. So 3D NAND, of course, because it's on 3D dimension, had a lot of complexity, cost, and the lithography limit. So now we are reaching this scaling wall. So research now start to evaluate, to work on new physical storage mechanism, for example, phase change memory, introduce ferroelectric layer in the device, or resistive memory that slowly emerge, and for example, fast change memory have been introduced by STMicroelectronics last year. So we are slowly moving from flash to other type of device. However, flash memory have really powered the data revolution, again from USB drive to data center. And this success is well illustrated here. Is a decade of both material and process optimization innovation. So from the first floating gate MOSFET to the very complex 3D NAND structure. Now we have 200 layer, stacked layer, one on the other one. But after this almost 4 decades of optimization, now further gain are increasingly incremental, meaning we need we cannot shrink the device indefinitely, and we are reaching a point where each extra byte store require exponential cost, but also energy. So now, as introduced here, at the very end of this hierarchy, we can lay DNA. So most of you know that better than me. DNA is a natural polymer capable of encoding on the paper massive information at the molecular level. So we may shift for a new frontier, moving from semiconductor bit to a biological base. So DNA storage work by translating binary data into a nucleotide sequence, so basically A, T, C, and G, and information is written through DNA synthesis and can be read through sequencing. And here we are leveraging a decade of biotechnology development. Currently, the challenge is not, or maybe less, in the reading, because currently sequencing has become quite fast and quite cheap. At least it's cheaper compared to, here the real bottleneck of the technology is the writing of DNA, at least at the same scale and speed that what is done with the sequencing. So starting from the beginning, the classical writing method, the phosphoramidite chemistry, introduced early 1980, so it's not new, which remains the foundation of DNA synthesis. So each base is added through a 4-step sequence, so deprotected, coupling, capping, and oxidation. So while it's achieved excellent accuracy, especially for short nucleotides, it's sequential, so in serial. And also it's consumed a lot of reagent. So cycling time of several minutes per base make it quite difficult to implement for large-scale data-oriented synthesis. Now, if we think to shrink the reaction sites, it will drastically reduce first the reagent consumption and the diffusion time, so accelerated each base addition step. So when here future reach the micrometer scale reaction, possibly complete very fastly, much more fastly compared to the minutes of process, while possibly thousands or millions of sites can be run in parallel. So this kind of approach now can make synthesis economically viable and scalable. So in essence, the miniaturization of this technology can transform DNA writing from serial chemical processes into a massive parallel information technology. So to write DNA strain in parallel, in short, we have 3 different possibilities. That can be done schematically by light, mechanical droplet spotting, or electrochemical control. So each technique offers distinct advantages. For example, optics have a clear precision, mechanics the flexibility, and electrochemistry the scalability. So the goal here is to find the good balance that combine, of course, accuracy, but also cost efficiency and massive parallel operation. So first, photochemical DNA writing. So the first large-scale parallel DNA writing use photolithography. This is well known in micro nano fabrication, where we use IV light through physical mask in order to activate specific site. So at that time, it was already revolutionary in showing that we can have thousands of sequences that can be synthesized simultaneously. However, we are in this first demonstration, it requires one physical photomask per nucleotide addition, that lead to complex and costly optics. But this first step, this approach, proved the concept, but lacked, of course, of flexibility when we have the application of data storage scale throughput in mind. Now, an evolution of this technique was to replace the fixed mask with programmable mirror, so enable to have a dynamic light patterning and faster cycle. So we can see some companies like Agilent or Twist using this to produce flexible custom DNA arrays. Yet, optical diffraction and photochemistry still constrain how small and how dense the unique feature can be. So this limit motivates exploring non-optical route. So the first non-optical route is a mechanical DNA writing, where mechanical spotting was one of the earlier alternatives to this photolithography base. So here the reagents are physically deposited in thanks to Finney nozzle, similar to classical inkjet printer, onto a specific region on a substrate. So this allowed flexible pattern and different chemistry, but also have some limitation. For instance, the droplet size, evaporation issue, which limit the precision and the throughput. But it remains useful for low-density custom array rather than high-volume DNA writing. And this technique still have a poor scalability, not beyond 10 to 5 sites. So here is an example of catalog Shannon instrument. One of the few existing industrial DNA writing system. So it combines both inkjet printing with enzymatic assembly using a workflow similar that we know in semiconductor photolithography, but on a macroscopic scale. So despite this very high throughput, the system is quite large. It occupies an interior laboratory room, around 20 meters square. And each printing feature is macroscopic on the order of, I think, hundreds of microns. So this is, again, excellent for batch synthesis, but not really for dense and localized, highly parallelized on-chip writing. Another mechanical approach uses microfluidics to directly to direct reagent to precise zones on the chip. So this approach offers good environmental control and because it's embedded some minimal contamination, but the complexity here leads to the valve network, which grows exponentially with the south count. So thousands of channels include alignment, leakage issue clearly become critical. So while this microfluidic is essential, for example, to bring reagent closer to the reaction site, it cannot itself scale to millions or thousands of parallel reactions. Now we move to the last possibility, electrochemical writing. So this technique uses on-chip small microelectrode to control the reaction by changing locally the potential and so the pH in the vicinity of the electrode. So this allows digital control of DNA synthesis using standard electronics, so eliminated optics or mechanics. So each electrode becomes, in this approach, a programmable reactor that we can address specifically the same things that what we have with a pixel on a display, for example. So in this approach, molecules, for example, hydroquinone, are oxidized or reduced locally to change the proton concentration, so change the pH. So the pH modulation activate on the surface of the electrode the DNA synthesis enzyme. So the reaction can occur in water, so make this process sustainable and compatible with biological system. And on the top of that, and this is maybe more important, the mechanism is completely driven by electronics, so possibly extend to CMOS integration. So here we have just a very short comparison of the different techniques. And what we can say is that combining this last technique, electrochemistry, with the very powerful CMOS technology, where we can miniaturize and parallelize at very, very high scale, can combine chemistry and electronic at the scale. So every electrode can be addressed through a chip circuitry in order to achieve the density and the precision that cannot be reachable, for example, by optics or mechanics. CMOS technology can be produced at scale, so to some extent at low cost when we are able to produce a large number of chips on the same wafer, thanks to industrial microfabrication. So this convergence, I guess, represents really the truly scalable route for large-scale DNA writing. So if we have a look on a specific interesting point, here the proton diffuse quickly in aqueous media, so created a spherical gradient around the electrode. And for micron scale site, steady state reaches very, very quickly in the range of milliseconds. Setting so the upper limit of a pulse frequency. So maintaining independent operation require, of course, optimization in the size, in the design, but also in the spacing in order to prevent overlapping diffusion from one electrode to the other one. So clearly there is a challenging and need to specific understanding of this technology, especially at that small scale. At micron or nanometric scale, the current depend linearly with the radius of the electrode, because the diffusion starts to be hemispherical. So smaller electrodes means faster stabilization, which is critical for high-speed and high-density synthesis. However, smaller electrodes, of course, generate a smaller current, which require very sensitive control at the electronic level. So here we have a trade-off between speed control and the CMOS electronic underneath. So in short, that can define the physical limit of electrochemical DNA writing speed. Microelectrodes are controlled like conventional digital memory. Each electrode corresponds to 1 bit at one time of chemical information. And by addressing through a CMOS driver, we can perform thousands or millions of reactions at the same time. So the chemical analog, like semiconductor data writings that we saw at the beginning of this presentation. So how it works? Here we have a cross-section of such a device. So the CMOS transistors are on the very beginning. We don't have to use very advanced technology. Now we are reaching 2 nanometer technology node. For this kind of technology, we can keep a technology node that we have access 10 years or 15 years ago for 60, 65 or 130 technology node. But that require stable technology. And the other challenge is implementation of the electrode technology, micro-nano electrode technology, on the top of the CMOS. So it's a monolithic integration. We start with the CMOS and then we integrate directly the technology step by step. Meaning the electrodes are fabricated after CMOS. CMOS is sensitive to, CMOS technology is sensitive to temperature. We cannot use high temperature level, so we cannot use 60% of the conventional process steps that are available in micro-nano technology processing. So this BL integration allows, on the other hand, electrical control without sacrificing the device performance. So this is a key engineering advantage over, again, a photochemical and mechanical system. With this kind of system, of course, microfluidic is mandatory in order to deliver reagent precisely on the top of the thousands or the millions of microelectrodes. But that drastically reduces the use of reagent. Finally, we need electronic control in order to process this parallel operation. So each electrode can be driven individually by on-chip DAC, so digital controller, that can be programmable thanks to some income information, pulse, amplitude, the durations, the sequence that have been encoded from the binary to the DNA style format. So this can lead to real-time encoding of digital bit into a chemical base. So this is not just science fiction. We can find in the literature some already existing demonstration. In fact, they are not very numerous. We have 2 to 3 demonstrations. So this slide summarizes the two main electrochemical demonstrations, both showing the first proof of concept, but still at a limited scale. So on the left, we have the Microsoft approach, which introduces nanoscale electrode wells. Here, each electrode in color have 650 nanometer in diameter and a pitch. So the pitch is a distance center by center between two electrodes. It's only 2 microns. So, however, in this demonstration, each electrode, we have just 4 identical sequences, so the 4 colors, that can be synthesized in parallel. So this is a first good validation, but with a limited scale. On the other one, we have this microelectrode array. So this is a Harvard demonstration. And this is the first demonstration really integrated on CMOS. In this case, the scale is much more relaxed because we have here the illustration of concentric anode and cathode pair that allow the localized pH modulation and also imaging. We have a pH sensor in the middle. But the size of this modulation is around 30 microns, and the pitch between two electrodes is almost 100 micron pitch. So it's quite large. So on this demonstration, only 256, I think, points have been done in parallel. However, this is the first fully CMOS compatible demonstration integration that shows the potential of electrochemical writing. So both of this approach demonstrate some local pH control through multi-site addressing, but the speed and the number of kilobyte per second range is still limited, mainly due to diffusion and not optimized integration. So what next? So prototype CMOS writer now control, we saw that, thousands of electrodes, and scaling to wafer level integration might unlock in the near future to reach gigabyte per day writing in order to bring this DNA storage closer to the practical integration. So here we will converge, we will have some fusion between nanoelectronics, electrochemistry, but also molecular biology. That might represent the next technological frontier for data storage. So just a last slide to summarize the main idea. As you both know, the data challenge demand new media, and semiconductor scaling can inspire molecular writing. In particular, thanks to electrochemical CMOS, we might be the only scalable path to have very high integration density, combining with a huge number of sites in parallel. And again, the key in the multidisciplinary electronics, chemistry, biology. Thank you for your kind attention.